Let's talk about torque and rotational inertia. Drawing parallels to the linear world, we know that a net force acting on an object results in an acceleration which is inversely proportional to the mass. In the rotational world, we have angular acceleration, which is the change in angular or rotational velocity with respect to time. In the instantaneous sense, it's d omega dt. So I'm assuming we have a good understanding of alpha, angular acceleration, and omega, rotational or angular velocity. So going back to the linear world, we know that an object in motion stays in motion if no outside force acts. An object at rest stays at rest, and that a net force acting on an object results in a change in velocity. That could be a speeding up, a slowing down, or a change in direction. So what is it? If an object is spinning, moving into the world of rotation, if an object is spinning, it will tend to continue to spin. Look at the Earth. It's spinning. It's not changing its rate of spinning very fast. It's an object which spins tends to spin at the same rate unless something acts on it. Well, what is that something? That's torque. So we have the relationship that the net torque acting on an object will result in an angular acceleration, in a rotational acceleration, which is proportional to the net torque and inversely proportional to the rotational mass. So what we need to explore here is, what is this torque that causes a rotating object to change its rate of rotation? And what is the rotational mass that tends to give an object rotational inertia, that tends to keep it spinning, or that resists any change in its angular velocity? It resists being accelerated. So in class we saw many examples. The torque, how much torque we get, does depend on the force, but it also depends on the placement of the force. And by placement we mean the distance from the axis that they're rotating, that we are rotating about, to where the force acts or where the force is applied. It also depends on the angle. So we know that in class we know that it depends on the sine of theta. So if I have a bar which is rotating about an axis here, if I want to get the maximum twist, so we thought of force as a push or pull, we can think of torque as a twist, a twisting force that tends to change the rate of angular velocity. So we can think of many examples. If the distance from the axis to where the force is applied is 0, the torque will be 0. If the angle between, if I pull on the bar this way, then the angle between the distance d, that would be this vector, d, and the force, in this case, are 0 degrees, and the torque will be 0. You can see this leads to no twisting. if we want to get the maximum twist, we want to pull in a direction, apply the force in a direction perpendicular to the distance vector, the d vector. So remember, d, I'm not going to write this down to save screen space, d is the distance from the axis to where the force is applied. In this case, the force is applied here at the end, so the distance is half the length of the bar, and to get the maximum torque, I apply it at an angle of 90 degrees, and that gives me the largest that the sine function can be, 1. And so in this case, the torque would simply be that distance times the applied force. Now, how much rotation I get, so I can adjust the torque by adjusting the angle, adjusting the distance, and adjusting the force. All three of those things will determine how much twisting force I get. But how much acceleration will I get also depends on the mass of the bar. So in class, we had 2 bars. They look the same. If you shake them back and forth or throw them in a straight line, they'll feel exactly the same. If you put them on a scale, they'll feel exactly the same. But if you grab them in the middle and try to twist them, they're quite different. And why are they different? Because the rotational inertia, the I up here, that depends on the mass and the placement of the mass. So in one case, although you can't see it, there's 2 slugs of mass located right at the center of the bar. And in the other case, the 2 heavy slugs of mass are located at the ends. So when mass placed far from the axis leads to more inertia than mass placed close to the axis, this being the axis of rotation, where we place our hand and try and twist the thing back and forth. That leads to our equation, which determines the rotational inertia. Rotational inertia for a point mass, we could consider these slugs almost point masses, is mr squared, where m is the mass of the object, and r is, like the d, distance from axis to mass. Just like the d in the torque equation is the distance from the axis to where the force is applied. Now, if an object has several masses, like our rotational apparatus, or the rotating bar mass system, where we have a bar rotating about the center, and we place cylinders on the bar, then the inertia of these systems is determined by adding the inertia of all the pieces. And if the masses are small compared to the distance from the axis, so this would be the r, this would be the m, and the rotational inertia of that particular mass would be gotten through using that equation. Same way with this mass. This mass is fairly small compared to its distance r from the axis, and so we could get the rotational inertia of this mass by using this equation here. The bar, on the other hand, the mass is spread out, and there's a way of computing that that needs to be covered in a separate lecture.